Good afternoon, everybody. It's Joe Drumgoole here, broadcasting from MongoDB's European headquarters in Dublin. This is the last episode of the Back to Basics series. Congratulations to everybody who's managed to last through all 6 episodes. I'm sure you're bored to death of my voice by now. We're going to give you a good break. There's going to be more webinars on slightly more advanced topics coming up in September, October and November, but we'll send out more details about them now. So I should keep your attention for just about half an hour or maybe a little bit less. A word from our sponsors. MongoDB Europe is happening in London on the 15th of November. It's going to be our first European-wide conference. This is a great opportunity to learn about MongoDB in depth and get some insights into what our future plans are. I do recommend you come along. I doubt you'll learn more about MongoDB in one day than you will in the rest of the year than at this event. And we're offering you a special discount. We're still on early bird registrations, and the discount code JD20 will get you 20% off that early bird registration. So do come along if you can make it. It's going to be a great day. So this is webinar 6, production deployment. We're going to talk today about some of the issues confronting you as you move out of development and start thinking about how you're going to run MongoDB in production. Within this talk, we're going to talk about a couple of things. But before we get into it, I just want to give a quick recap on what we've covered in the last 5 episodes. We've taken you from basic introduction to what NoSQL is and reminding you that MongoDB is a document database that stores JSON documents. We showed you how to build an application using CRUD operations and indexes and explain. We then went through some schema design. Then more recently we talked about the more advanced indexing types, geospatial and text indexes. A couple of weeks ago we talked about the aggregation framework, the way to do dynamic transformation of your data within the database using all the power of our database engine. And then webinar 6 today is going to talk about the process of taking a development project and making it available to end users. Now, there's a huge amount of work in taking a full-blown, full-stack project live. We're going to focus, obviously, on the database perspective, and the key concerns there are durability, making sure that our data is safe and durable once it's stored in the database and we can survive disk, rack, data center failures, ensuring that the system scales effectively so that we can handle the growing load. If we move from 1 to 10 to 100 to 1,000 to 10,000 users, can the database accommodate that growth in load? And of course, something very close to our minds in this modern internet world, data security. We've got to protect our users and our users' data from prying eyes, from hackers, and from people who would want to use that data in illegal ways. So we want to secure the data in our database. And security is not just at the firewall. What we've learned, if we've learned anything in the last 10 years, is security must be in depth. You must make the assumption that even within your firewall there may be people and programs that are trying to attack your data. So building in security from the database out is the best possible way to secure that. Finally, we're going to cover off some general production notes, which are general guidelines that we talk about in terms of deploying MongoDB in production. These are all documented on our website on a per-platform basis. So if you're running on Windows or a different version of Linux to the default one we run on Amazon, you can get those notes there. We'll also show you some of our automation tools to help automate building this stuff. And then at the end, we'll wrap up with a quick Q&A. So the first thing is durability. How do we handle the challenge of keeping our data safe? Well, we talked about this in the first slide deck, which I'm sure, or the first webinar, which I'm sure people don't recall. We create durability in MongoDB by making replicas of the data, and you can make up to 50 replicas of the data. Not too many of our customers need 50 copies of the data, but we do recommend you start with what we call a 3-node replica set. So essentially 3 copies of the data. And obviously you want to isolate these replicas, these nodes, as much as possible as you can. So keeping them on separate VMs or separate operating systems for sure, but making sure that the underlying hardware is isolated as well. Otherwise you're creating single points of failure. So 3 separate nodes running on 3 separate operating systems, running on 3 separate pieces of hardware. And of course, if you want the ultimate in data isolation, in 3 separate data centers, or at least on 3 separate racks within the same data center. If you're running in Amazon, deploying your nodes in 3 separate Amazon regions makes a huge amount of sense to insulate yourself and guarantee that you're not tied to any single points of failure within Amazon. So 3 nodes is our baseline. You can go to up to 50. Some of our largest customers want a copy of data in every data center, and they have 50 data centers. So we actually increased that number in the last major release of MongoDB. So now you can support 50. So what does a replica set look like? Well, we start with 3 nodes, and we tell the replica set, you're part of a replica set. Each node is made aware of the fact that it's participating in a replica set by running what we call an RS initialize command, which tells each node all the other members of the replica set. So the first thing they do is they elect a primary. So each of these nodes talks to each other via a heartbeat protocol that we define internally, and the 3 nodes set about establishing which one of the nodes is going to be the primary. And the primary is the node that will accept all of the write operations to this collection of nodes. So when you're writing to a replica set, you're always writing to the primary. Now, you don't need to know which node is the primary. Your driver will establish that. As long as you connect to any node in a replica set, the driver code is designed to identify the primary automatically. And there's a full spec for how to do this, which we'll get a link to at the end of the talk. But the key thing is you don't need to know which one is the primary from a client's perspective. From the server perspective, it needs to know which node is the primary because that's the one that's going to take the writes. The primary then replicates to the secondaries, right? So effectively what happens is writes go into the primary, and we have a complete protocol to replicate all the data that's written to the primary to the secondaries. We actually use an internal MongoDB collection called a capped collection, and we use a tailable cursor on this collection to essentially get all of the updates automatically. I think I talked about tailable cursors way back in the day. So essentially each node that's a secondary, and you could have up to 49 secondaries, as I said, will take a copy of the data and make a copy in its local disk or wherever the disk storage is allocated for that secondary. And so this system will run forever. And there's a set of heartbeats that pass between the nodes that essentially tell us that all the nodes are up and running and connected. Now, what happens if the primary fails? So your Amazon node collapses, or somebody kicks out the power supply, or the disk fails, or your operating system crashes. Any number of things can make a node effectively drop out of the replica set. So what happens is the heartbeat detects that there's no primary, right? So now we know we've only got 2 nodes. So for the moment, there's no primary. Now, in the event that your client is trying to connect to this replica set and do a write, it will get a write failure. If it's trying to write just at the point where the node fails, it will get an exception. It's your job as programmers to handle that exception, but you only need to handle it once, because as you'll see, one of the things that the client will do is now elect a new primary, and the second write that you attempt will wait for this primary election to complete for some period of time. So effectively, if you're writing code and you get a write error when you're doing an update or an insert, you catch the connection failure, and then you just try the rewrite once. If the second rewrite fails, then you've got a more critical failure with your replica set. So what happens is the 2 remaining nodes then have an election. They have a majority, and one of the key things for election to succeed is a majority of the nodes must remain up in the replica set. Now node 2 decides to be primary, and the way they decide which one is the most relevant is essentially which one has the most up-to-date copy of the data. So node 2 had the most up-to-date copy of the data. It then effectively becomes the primary and replicates that most up-to-date data to the secondary. We now have a stable system again. Now, if the driver has been waiting to complete a write, it will now complete that write on the primary. So your your try-catch will essentially complete the write, and then you carry on as before. If for some reason you couldn't elect the primary, then the driver will again have a second failure, and at that point you have to re-raise the exception to the application, because it's not something you can recover from. So now you need to take other steps. What happens when an application can't connect to the database? It may be that you invoke an operational procedure, or you essentially hold rights in a queue. It's up to the application to decide what to do when the database is not contactable. And this could happen if, for instance, you were running 3 nodes in a single Amazon region and the region went down, right? That would cause all of the nodes to be uncontactable, in which case you'd get a second write failure. So now we have a stable system, but we still want to return to what we deployed in production, which is 3 nodes. So in this situation, we go and we rectify the error that caused the primary to fail originally. So that would involve running some diagnostics, or essentially seeing about the liveness of the node. There can be any number of reasons a node failed. So we establish that we've repaired the problem. So we might bring up a new Amazon node. We might replace the power supply. We might reconnect the network. So node 1 will now rejoin the replica set. Remember, it knew already it was part of the replica set. If you're rebuilding a node from scratch, you would essentially give it the replica set name and it will rejoin automatically. What it now needs to do is catch up. It now needs to understand, what did I miss while I was down? So it will ask the primary to give it a copy of all the data it missed, and this is all timestamped data. Now, in a situation where the node has been down for a long time, what may happen is that the node 2 oplog, the list of operations that were queued for replication, may have rolled over. In that scenario, what we can do is we can do a resync, where essentially we take a complete copy of the data from the primary. And in those scenarios, it may be quicker just to take a copy of the data file from node 2 and drop it on node 1 and allow it to resync from there. So that will give us essentially the ability to recover node 2. And now, at the end, we've got 3 nodes again. Note the primary stays on node 2. The whole point is the primary can move around the collections of nodes in the replica set. There's no problem with that, because remember, the drivers, the client software that we provide, is completely comfortable with establishing which node is the primary given any node in the replica set. So you don't need to worry about that. So now we've got a recovery. Note that the node's moved. If we wanted to make node 1 the primary again, we could change its priority to essentially make it the most likely to be elected, and then force a re-election, in which case node 2 would essentially drop out, would drop down from the primary, and then we would escalate node 1 to being the primary. Primary elections will always cause a slight delay or a connection failure with any writes in progress, but as I've said, as long as you've got single recovery, as long as you can catch that connection failure exception in your code, in your Java or your Python or your Ruby, and retry once, the driver is designed to queue that second write until the node recovers. And there's a timeout period called server timeout that will essentially define how long you want to wait there. And that's something you have to decide on. If your client is very far away from your primary, you may want to make that server timeout very long. If your client is very close to your primary, you may want to make it a shorter period. And that's something only you can decide. So there's a second aspect to replica sets, what we call tunable consistency, right? This is a function of how up-to-date and consistent do you want your reads to be, and also how concerned are you that writes succeed in the face of failures or changes in configuration or changes in the system's topology. So strong consistency, we make all applications read and write from the primary. And if you always read and write from the primary, you're guaranteed to get consistent reads, which is to say you will read what you wrote. So the key thing here is lots of NoSQL engines get their performance from being eventually consistent. So if you write a record and then you read that record immediately, you may get stale data from the previous write operation. That can't happen in MongoDB because our strongly consistent constraints on the primary guarantee that your data is updated effectively. Now, you may choose to read from a secondary. And you can choose to do this for a number of reasons. You may want to have read access that's local. So you might have a primary in London and secondary nodes in Tokyo and New York. In that scenario, you may be willing to read eventually, effectively get older versions of the data in order to improve your read latency. So we have a very large banking customer that distributes book data, essentially all the transactions that are being processed. When you want to read that data, you probably can actually be comfortable with not getting the last minute or two of data, but you do want to get your reads to complete fast. In that scenario, they read from secondaries which are local to the business offices that they're working in. And so they trade consistency. They trade strong consistency of their reads for a low latency on the reads. And in that scenario, they read from a secondary. And of course, as I said, you can have one secondary per data center if you want, or per office, up to 50. So you make a choice, highly consistent reads and writes from the primary, or eventually consistent reads from any one of the secondaries. But there's more. We can also control how much we care about writes. So if you're writing a logging application where it's absolutely irrelevant if you miss a couple of logs, just as long as the bulk of them get through, you can set the write concern, which is applied at the write operation level, to 0. And effectively, write concern of 0 says, once the packet leaves the driver, I'm done. I return in the loop. And of course, that will be very fast because we're not waiting for a round trip from the server to acknowledge that the write is being received by the server. On the other hand, if there's a failure in the network between doing that write and the write reaching the server, or if the server fails before persisting that write to disk, you're never going to find out about that because the client has not asked for any error control. We do not recommend write concern 0 for anything but the most volatile, least concerning writes. If you're writing log data and you really don't matter about losing a few logs. On the other hand, if you're writing any kind of data that's of value to you, you want to look at the higher levels of write concern. Write concern of 1 will say, please return any errors generated by the server. And write concern of 1 will give you one of the most important errors you need to trap, which is duplicate key error, where I'm writing an object and it already exists in the database with a unique key on the index. You'll get those errors straight away. You'll also get socket errors and errors between the client and the server. So if the network drops, you'll get an error there. And then finally, write majority. I can see I've left a little bit of text off this here. I'll fix that before we send out this deck. Write majority is the one that we recommend for production deployments. And that is effectively guaranteeing that the write succeeds on a majority of the nodes. And in that scenario, what we can guarantee is that you've got replicas of the data written before the write operation returns to the client. If the write to a majority of the nodes fails, you'll get an error, and again, you want to do a retry. If the retry doesn't succeed, then you know there's something significant up with the cluster, and then you need to re-raise the error to the application. We also control journaling, which essentially tells us how fast we write to a journal before we persist the writes to disk. And journaling is simply an on-off switch. It's more relevant for people running mmap version 1, which is the old storage engine. It's less relevant for Wired Tiger, our new storage engine, which actually journals its data internally. So what does this look like? Well, with tunable consistency of write level 0, effectively the driver sends the packet and then it's done. We don't do any error checking. It may reach the primary, it may not. And it's only applied in memory when it reaches primary. We don't look at persisting to disk or to the journal. On the other hand, with write 1, we write to memory, but we also check for any errors when that write occurs in memory. And most typically, you'll get index errors, or you may get an error because there was a syntax problem, or there may be other constraints that you breach. Then with journal, we apply in memory, we write to the journal, and then we return. And in this case, with a single node, if you're running a single node server, and that's obviously not something we recommend in production, you'd guarantee that that write was persisted to disk somewhere before you returned. And then the final one, the one we recommend for most production deployments, is W majority. Here we write to the primary, we apply in memory and disk, Then we write to the secondary reply in memory and disk. Both those writes return, and when they return, we know the write is safe. Obviously, with this kind of write, we've got to wait for 2 write operations to occur in parallel. So it's going to take a bit longer, but at the same time, we guarantee more high durability. So what we recommend for almost all the production deployments we see, what we need is to have a write concern of majority. There's very few mission-critical applications where write majority is not the right selection for you. So if you're not using write majority, you have to think very carefully about the use case and what you're expecting from the application. Can you survive losing writes? Can you survive getting data that may be out of sync because you've lost some records from a previous write operation that didn't succeed? So this gives us data durability. This is the replica set, and it's the fundamental basis of a vast majority of production deployments, because a single primary on a heavily configured server with lots of memory and lots of CPUs can take tens of thousands of writes a second very comfortably. So you want to have a lot of traffic to exhaust the capabilities of a single server. But you'll notice that we are tied to a single node. The primary is a single node in your cluster. And as we all know, there can be problems with running everything through a single node in write performance terms. And to fix that, we offer a sharding capability that partitions the load. So sharding gives us the ability to address I/O bottlenecks. If the network traffic or the disk traffic on the single primary is saturated, it allows us to partition the load across several primaries running in parallel, and we'll show you how this is done in a minute. And of course, memory is the other bottleneck. For any database to be performant, and MongoDB is just like all the rest, we want to keep all of our indexes in our working set in memory. If the indexes in the working set exceed working memory, then now writes and reads are going to have to reach down to the disk. And if accessing data in memory takes 5 minutes, accessing data on disk takes 7 months. It's way slower. You really want to avoid hitting the disk for the majority of your operations. Otherwise, you'll see a massive degradation in performance. And the way we do this is with a sharded cluster. And a sharded cluster effectively builds on the replica set technology. So each shard in a sharded cluster, and you can see this is a shard here. This area here. Sorry, let me just get my pencil up. This is a shard. That's a single shard there, and there's another one here, and we carry on as before, right? Each shard contains a complete replica set with a partition of the data. And the partition of the data is defined by the partition key or the shard key that essentially divides the data up amongst the replica sets. And then we have a set of MongoS daemons that run in front of the MongoDs that manage each replica set. And the MongoS's route requests to the relevant partition or shard that essentially covers and controls the data. And the way it does this is by using another replica set called a config server. And the config server is essentially the address book for the cluster. It tells the MongoS's, which are essentially dataless routers. MongoS stands for Mongo Shard Router. Where is the data for this query located? In the event that you don't use a shard key, the MongoS will do a scatter-gather query across all the cluster members, and that's expensive, so we don't really want to do that if we can avoid it. And that's why we want to use the shard key in all queries when we're running a sharded cluster. And again, as before, the driver manages the interaction between the MongoS's and the primaries. And if a MongoS drops out in the middle of a request, you essentially do a single retry, and that retry will find a new MongoS to send that request to. You can run as many MongoS's as you feel necessary to handle the load of your system. These are dataless servers. So in this scenario, I've got 3. But you might run 1 MongoS per application server. You might have more MongoS's than you have shard members. You might have less MongoS's if you've got less clients, but there's a very large amount of traffic from those clients. Defining the topology of your sharded cluster is one of the things that we recommend you contact MongoDB. If you're deploying a sharded cluster, we can really help you to do this. We have the expertise. We've done it thousands of times Every individual pre-sales and salesperson has been involved in hundreds of sharded deployments. If you're doing it for the first time, it's very easy to get this stuff wrong. Selection of the shard key that partitions your data, very easy to get wrong. And trust me, you don't want to get this wrong, because if you get the shard key wrong, you have to reload the whole cluster from scratch, because the shard key is immutable. Now, setting up replica sets and sharded clusters, absolutely you can do this manually, and there is deep documentation on our website about how to do this, but there's a lot of manual steps. With a 50-node replica set, you've got to log into each node and configure each replica. Don't do that. We have automated tools to allow you to do this. We recommend you go, in the simplest way, use our cloud service, MongoDB Atlas, to get up and running in next to no time at all, right? Or if you don't want to run on a cloud and you want to run in your own Amazon cloud or indeed on-premise, you can still manage that cloud from our SaaS-based cloud manager that essentially allows you to manage cloud deployments online, but still having them hosted on your own premise. Or if you can't have management tools sitting outside your management domain, lots of customers want to have complete control of all the data, you can take a copy of our cloud manager tool and run it on-premise, effectively using all of the capabilities of Cloud Manager, but running as a suite of servers inside your own data center. So we have lots of options. Our database as a service with MongoDB Atlas, Cloud Manager, which essentially allows us to run inside our own cloud service, but have your nodes running in whatever data center you want, or Ops Manager, which gives you complete and total control over the environment in your own data center. Or you can do it all yourself with scripts and manual steps. And there's very good documentation on this, but trust me, don't do that. Don't make it hard on yourself. The last thing you want to be doing is manually deploying and upgrading clusters. We have all the tools for this, and it's from the company that built MongoDB. And if you get these tools, you'll have the support you need to understand how to manage it. I'm just going to give you a quick look at Atlas and the Cloud Manager. Allow me to share my screen. So we can see here, this is the Atlas environment. I've got a cluster up and running here, but I could add a new cluster very easily. So I'm picking the AWS region, which is EU West in Ireland. I'm then going to scroll down and pick the size of cluster I want. So I might pick M10 because I'm just doing a demo, and I can increase the storage there. And you'll see over here on the left, we're getting a little price value. So it tells us how much I'm going to spend. So if I reduce the storage, the cost goes down, right? And I can just choose to use encrypted storage volumes in Atlas if I want. And you can see these are all of the instance types that you can use in Amazon. So you can go up to M100 instances. Now you can see the price goes up appropriately when you set these up. And then I can choose the replication factor. I'm going to default to 3 nodes, but I could choose 5 or 7 nodes. I'm going to stick with 3. I don't want to build a sharded cluster, but I could, like just selecting this on rather than off. And do I want to enable backup? Yes, of course I want backup. Why do we want backup? Yes, we're replicating all of our data, but backup is there in case we screw up. So imagine I build a cluster and everything's up and running, but I deploy a version of my software that destroys the data in the database. Well, all the replicas will replicate that error. In that scenario, you must have backup. So once we're up and running, I can now say confirm and deploy. It's going to cost me $72 for 30 days, which I think is a cheap date for setting this stuff up and running it inside Amazon. And I can do confirm and deploy. Oh, I need to change the name. Let's call it cluster 2. And I'll do confirm and deploy. And that's going to go and set up my second cluster. And you can see there's a replica set here being configured, and it'll tell you at the top here we are deploying your changes. Once you've got it up and running, you can ask for connection. It will give you a complete connection string. Sorry, it scrolled down there a little bit. So in here is the complete connection string, and I can show you how this runs. Again, I've got a terminal here, and so I ran this connection string earlier on. and I'm now connected. And I can use this as before, so I do show databases. And I've got a little demo database here, so I use demo. And I can do db.demo.insert A:C. And there we go. And I can do db.demo.find, and you'll see I inserted a record here before. And there we go. I mean, we were up and running. We have a cluster running. We have inserts. We've got the shell running. This is running this shell is running inside Amazon. One of the things you'll find is if you connect to a cluster in Atlas and you're running from your local node, you need to change the server timeout value because the latency between your local client and the server is too long for a standard connection. It'll just time out. So what I recommend is when you're actually interacting with your cluster, you actually just shell into an Amazon node that's on the same region, and then you'll get the performance you need. But very quick to set up. And you'll see here we've got rewrite operations and IOPS and a bunch of data here. And this node's still setting up, which is why I set this other cluster up beforehand. Now, you may want to just do this on-premise. So I can do this on-premise by using Cloud Manager and say build a new deployment. And where would I like to deploy? So I could create it locally on my laptop, deploy locally, deploy in other remote, which is some other, it might be in my private data center, or I can choose a cluster provider like Amazon or Azure. And so if I said deploy locally, create replica set, I'd give it a name, new set, how many nodes, I could go from 3 to 5 to 11. The data prefix is default, and I say continue. Would you like to use Cloud Manager to backup? Yes, I do. And then it just tells you to install the agent, and it'll give you a whole set of instructions for Mac OS here, and it tells you how to configure and install the agent, which I'm not going to do now because it takes quite a bit of time. The point is, these tools are available for you to use today. So, my advice to you is use our automation if you're going to use these tools. So, the other thing we want to do is make sure we've got data security. We have given you a whole range of tools in the database to make sure that your data is secure. So for all your clients, make sure you use SSL for all connections. This is provided in all the drivers as out of the box. You can do it in community. You can do it in enterprise. Make sure you've got users and passwords and access roles for all your databases. Again, this is all provided out of the box by MongoDB. Don't be setting up databases without usernames and passwords. One of the nice things about Atlas is it demands that you provide usernames and passwords and roles for the database to ensure security. If you're going to keep encryption, or you're going to keep in credit card and personally identifiable information in your database, you really need to think about our encryption on disk capabilities to store that data and make sure it's safe from somebody stealing the raw disk files. This is one of the most pervasive attacks we see on database systems. People hack into your nodes. They don't even bother trying to get past the username and password. They just get an access to the physical node or the virtual node that's running the database, and they grab the database files. In that scenario, if you don't have encryption on disk, you're guaranteed to lose and have all of your data exposed online. So it's increasingly becoming a mandatory thing for lots of our customers who have personally identifiable information to use encryption on disk for this kind of data. You also want to turn on audit so you know who's changing what. One of the classic attacks is to find access rights and change the control and access rights so you can access the system from the outside. You want to understand that. Make sure the monitoring is turned on for all your nodes to identify unusable information, right? So you want to look into your nodes and make sure they're not doing things you don't expect them to do, right? So we want to see operations happening from different locations you don't expect them and detect that and essentially respond to it in real time. And don't make your databases globally accessible. There are lots of controls inside the database system to control the IP addresses from which clients can access your database. do please use these to control so that you don't have somebody coming in from the outside. Now, last thing, some general production notes. Again, these are all documented on our website, but use the most recent release. Make sure it's properly patched and up to date. More importantly, make sure you picked out all the patches for your current release. Use the Wired Tiger storage engine. It's our default and will give you the best performance possible to ensure that you extract the maximum value from modern clustered systems where we have a high memory footprint and a high number of CPUs. Make sure you pick the most appropriate write concern for your application. It's almost always write concern majority, which means that the writes percolate to a majority of the nodes before the client gets a success code returned. Each of our drivers has connection pools built in. Make sure you're setting up that connection pool appropriately to match the server load. If you have thousands of requests coming in per second and your connection pool is very small, they will be waiting for connections to become available. So tune your connection pool to about 125% of the expected connection load. Make sure you've got sufficient RAM and CPU. One of the ways in which we generally get surprised by modern database systems like MongoDB is they're more CPU than disk I/O intensive, and they're more RAM intensive. Make sure you understand your working set and you've deployed enough RAM and CPU to handle the workload you're expecting. We prefer solid-state disks. Well, surprise, surprise, they're going to remove a lot of the latency. If you've got high write demand applications, writing to SSDs is thousands of times faster than writing to spinning disks. Disable NUMA, non-uniform memory access. For lots of systems in which there are multiple cores, they have allocation strategies that give you memory close to the core that has a lower latency than memory far away. The problem is when you're running a database server, the memory accesses are distributed randomly across the cores, and with NUMA what happens is you saturate core 1 with lots of the data. So NUMA wants to essentially distribute the memory across all the cores. Allocate swap space. If you don't put swap space in your system and you run out of memory, the Linux OOM daemon will kill your process. Swap space will mean you run slower, but at least you get to detect that, and then you can look at addressing it in terms of memory and performance. Look at the Wired Tiger compression options. You can turn off compression. We absolutely do not recommend that, because it obviously has a huge impact on the write performance. You're writing uncompressed files which are much larger. The default is snappy, but if you've got a low write rate but you want to make sure that you optimize the storage on disk, you can choose Zedler, which gives you much higher compression performance. We recommend the XFS file system. It gives the best possible performance for database engines writing to Linux systems. Time synchronization is critical. Having the same time across all of your systems makes life a lot easier, especially for logging and for managing uptime and for managing issues across systems. NTP should be deployed across all your systems with a single time sync. You want to turn off the A-time option for all file systems storing database files. We don't care about the access time for files. All of the interesting stuff that happens in a database file happens internally. Make sure you have the file descriptor limit increased to the level of connections you expect. The default file descriptor limit on most Linux and Windows systems is too low. You need to bump that up. And then avoid NFS. We never recommend NFS for using database files. There's all kinds of issues around data consistency with NFS. But more importantly, try and avoid systems that provide replication themselves, because you're double replicating. The replica set already replicates the data. Now if the database writes to the raw files are also being replicated underneath by a SAM, you're taking a huge performance hit there in terms of excess replication. So lots of traditional businesses have had SANs for running databases that are not effectively replicated. So your more traditional MySQL, Postgres, Oracle databases depend on the SAN to give them fault tolerance over their database files. You don't need that in MongoDB, and more importantly, you'll pay an extra price. So that's pretty much it for the webinar series. I want to leave you with 3 messages before we finish up today. Before you go live, come and talk to us. We've done it thousands and thousands of times. We can help you make your production deployment successful. We have a very simple package we can offer to any user called a health check that will essentially, an assured MongoDB professional services engineer will visit your deployment or remotely log in and validate that it's properly configured for production deployment. It takes about 2 days. It's a fixed price. You can contact us for pricing on that issue. Very easy to do, and it's a one-shot thing. Trust me, it'll save you a lot of pain. Do use our automated tools. Atlas and Cloud Manager will make your life much easier. And I'll leave you with one message. Most production problems happen because the customer tried to go it alone. MongoDB absolutely makes life simpler for you, but deploying a large-scale production deployment of any system, you're really, really making it hard on yourself if you don't work with us to make sure that's successful. So, with that, I'm going to have a quick look at the questions and see if I can cover off some of them. So, Krishna Kumar asked, we want to have 4 months data retained in production after which we can purge. Time to live is one option approach to that requires just an index creation and no code change. Is this a recommended approach? There's a couple of ways. If you want to do replication, I would say what you do, Krishna, is you write to the data. You write that you configure a separate set of collections. Each collection has 4 months of data in it, and then you roll over to a new collection. So effectively, each collection has 4 months of data, and once 4 months has gone by, the older 4-month collection can be dropped very efficiently, as opposed to trying to purge date-stamped records out. So I would say keep one collection for every 4 months, or every month if you want, and effectively you can roll out the older collections over time. So use collections rather than time to live. Time to live is not really designed for that kind of archiving model. Silpa Jane, how the election happens for the primary node. Do we still need to do some? Primary elections happen automatically, Silpa. You don't need to do anything. As long as the majority of nodes survive any kind of failure, they will elect a new primary and everything will carry on as before. The only thing you need to do from an application perspective is to catch that first failure, which will typically happen if a write is in progress when the primary fails. By the time the primary comes back, your client will wait for a certain amount of time. And like I've said, if the client is far away or it's willing to be more resilient, you can set that server timeout to a longer period. Michael McDonald asks, if total resync is necessary after node failure, is the file move done automatically or does it require the user intervention? How will you know the logs have been overwritten and files? Michael, you can just bring up the cluster member and it will automatically do the right thing. If it doesn't have, if you run off the end of your op log, it will resync automatically. I'm just saying that in some scenarios you may want that resync to happen faster, in which case you can manually copy the data yourself. But the node will recover at its own rate by using the resync protocol automatically, so you don't need to do anything. Shukrat Nekbaev says, J-True, writes do not need to persist to the journal. Isn't true means innate? Yeah, writes will persist to the journal with J equals true. The only thing I'm pointing out is J equals true was more relevant for the mmap v1. Internally in WarTiger, the journaling happens anyway, whether J is true or not. Himanshu Karki says, during a primary down situation when a new primary has not been created elected, what happens to transactions currently being performed? If there's a write in progress, the write will get a connection failure and then you retry. With MongoDB 3.2, elections should never take longer than about 3 seconds, and the client is designed to wait for that amount of period to expire. So elections should never take 40 seconds. If your elections are taking 40 seconds, there's a configuration issue on your cluster and you need to look at that. We don't expect elections to take 40 seconds. 3 to 12 seconds would be the absolute max, and most elections happen faster than that. Again, it's a function of how far away you know. If you've got a cluster which is separated geographically by a WAN, obviously elections will take longer because the election protocol has to execute over a wide area network. If, on the other hand, your cluster is in the single data center, then it's going to happen faster. And again, you can use server timeout in the client to control the access times. Venkata asks, can we take backups to stores at shard level rather than complete collection level? Venkata, you absolutely can, but you have to use our backup tools to do that. Cloud Manager or Ops Manager will allow you to back up at shard level, basically backing up the whole shard cluster. Venkata also asks, what tools do you recommend for MongoDB developer and support guys for monitoring once we productionize? Ops Manager and Cloud Manager have all the monitoring capabilities you need for all of the cluster. I didn't show them in the demo, but they have a complete monitoring framework where you can set up alerts, pagers, emails, and SMSs to give you alerts when particular failure happens. Venkata asks, will performance come down by using encryption? We typically find for most clusters, the encryption overhead is less than 5%. Typically you have a fair bit of CPU available, and particularly using Snappy. And so what we suggest you do is benchmark your own environment and see what the cost of encryption is. But it's turned on by default with Snappy, so when you're testing, you should be testing with Snappy encryption. If you're getting the performance you need, then you don't have an issue. Dan Freer asks, is encryption on disk a Mongo function, or do you mean user-controlled encryption? Encryption on disk is a Mongo function. It's part of the WiredTiger storage engine capability. It's something you configure. It's in our Enterprise Advanced solution, so you need to pay for it. You can't get encryption on disk on the community version. Shukrat, could add disable, yes, you can. Same thing as Numa, yes. Disable transparent huge pages is the same thing. What is SSDs? SSDs stand for solid state disks, Silpa. Mark Liu, please ignore if you covered already. I came in late. How does MongoDB conform? We are absolutely custom built for a distributed virtual environment. I haven't gone through the details, but if you look at our production notes for VMware, there are some specific guidelines to follow with how you would configure a MongoDB environment for VMware deployments. Satya asks, is it out of scope for this webinar, but is there a process to force the user to change a password on initial login as the admin sets the password for the user? I'd have to check that, Satya. I don't know, but typically this is not a user login, it's a login from the driver. The driver is what logs into the application, so it's programmatic. So poking a driver to say, please change your password doesn't make a lot of sense. Krishna Kumar says, thanks. Do we have to manually delete the collection after 4 months? Yes, you do. We won't help you with that. That's an application process. Satya asks, if I make changes to the config file, should I restart the cluster in order to make the changes effective? Yes, you should. But again, if you change the config file, you can restart each node of a replica set individually, so the cluster itself won't come down. And that's the whole point of a replica set, is that it allows you to make configuration and management changes on each node of the cluster individually without taking down the whole cluster. Silpa Jane, does journaling reduce the performance of the database system? Do we need to keep it off by default? Every write to disk is going to have a performance impact, Silpa. So yes, journaling will have a performance impact. So I don't recommend you turn it off because it's a key part of the data redundancy and durability of the system. It's one of the prices you pay for ensuring you have durable data. Shubham says, I have an application where the data is written in huge bursts for a couple of days and then it remains silent for the next 2 weeks and the cycle gets repeated. Write throughput could go as high as 5,000 writes per second. Shubham, I don't want to burst your bubble, but 5,000 writes per second is trivial for MongoDB. I can get 40,000 writes a second on my laptop, running the client and the server on the same machine. So 5,000 writes per second, a single replica set won't even break a sweat with that. So I wouldn't worry about write performance in those scenarios. Venkata asks, is Mongo planning to introduce commit rollback functionality across documents in coming versions? Any plans, updates you can give us? What you're talking about here is transactions, and we've discussed doing something transactional in MongoDB world last year and this year. We make no commitments on future plans. We do know multi-document cross-collection transactions is something lots of people ask for. I can't make any commitments on whether we'll provide that. Yossi Hohash asks, does the driver seats on a different server from the primary? Yes, typically it does, Yoshi. It's a distributed database. Your driver is part of your application stack, and so typically runs inside your application server or in your application code base, which would typically, for a high-performance system, run independently of the database server itself. For smaller applications, you can run the database cluster and the application server in one box. Vargas, should we use MongoS's services on separate instances, or can we run them on shards? Don't recommend you run them on the shards, because the shard will go down at the same time as the MongoS. So we recommend separate boxes for the MongoS's. What you typically run the MongoS's on is on the same stack and nodes as you run the application server. Himansu asks, only during the failure new primary is selected as an application lifecycle, or are there some other instances as well? The only time you'll perrick a new primary is when one primary goes down. So you can take secondaries out of the cluster with no impact on the cluster's performance whatsoever, unless somebody is reading from that particular primary, in which case they'll have to do a retry. But yes, so it's only during the failure. You might want to take a primary down when you're upgrading the operating system, in which case you would step down the primary last, and obviously you want to minimize the downtime or the interruption to clients, so you'd pick the quietest time for your application. For some applications, there's never a quiet time, in which case you've got to expect that your applications are written to handle that single failure. So essentially when the client is connecting to the primary and it goes down, they'll get a write failure, a connection failure, then they need to do a retry, and by that stage you should be bringing up the new primary. Okay. That seems to be all the questions for today. We're going to send this deck out via an email. We'll include the links I've talked about today. I want to thank everybody for joining me, particularly those of you who managed to make all 6 webinars. God bless your persistence. We'll have a new webinar series coming up in the new year with some more advanced topics, and we'll let you know about that when it happens. Don't forget about MongoDB Europe. We do recommend that's one of the best places for you to learn more about MongoDB. And of course, if you're going into production, do contact us. We have offices all around the world. We can have somebody local work with you to make sure that your production deployment is successful. With that, I'd like to say thank you for all of you who've joined me today. And I look forward to talking to you on a webinar soon, or maybe even meeting you in person at a MongoDB user group. So with that, I will sign off and talk to you soon.
Thank you. Please stand